Okay, so good evening, students. Shahida has joined, and what about the other girl? Shall we wait for her?
Okay, miss.
Okay, we'll wait for some time because she usually joins. It's already 7:11. Okay, let's you watch the recordings. Okay, I'll start the class now. So last class we discussed about one's complement, two's complement representation, and in one's complement and two's complement, we also learned about overflow, but we didn't see deeply, right? We didn't have a detail. I didn't have give you a detailed explanation about what overflow means. So in this class, we'll see what exactly is overflow. Okay.
Okay, teacher.
Okay, 1 second. I'll have my writing pad connected. Just a second. Okay. So what is overflow? Overflow is nothing but it happens when the result of an operation exceeds the number of bits available in the register. Okay. So when we studied about memory, we also learned about registers, right? Register is a small memory unit that is present near the CPU. It is too small. And the values are stored in register for easier and faster calculations. So the register is very small. It holds at nearly 8-bit or 16-bit values. Okay. So overflow happens when the result of an operation, if we do an operation and the result, if it exceeds the number of bits, for example, if the register is 3-bit and the answer is something in 4 bits. So the number of bits exceeds. Okay. Only at that time, overflow happens. Okay. So let's get started now. Like, for example, while performing arithmetic operation in a computer, how can we detect whether there is an overflow or not? So let us consider an addition of two numbers first. Okay, we look at a overflowing in an unsigned number first. As you know, what is unsigned number? The number which doesn't have negative value, only positive values are used in unsigned number. So we'll see overflowing in unsigned number first. Okay, let us conditional answer. Two numbers. Okay, so as I told you, in unsigned number, we have only positive numbers. For example, let's take 7 plus 7. Okay, so how do we represent 7 in binary value? 7 is actually 1, 1, 1. Right? So when we add 1 again, 7 plus 7 is 1, 1, 1 plus 1, 1, 1. What is the answer? 1 plus 1 is 10, 1 carry up. So there is 1 carry here. Right, we can just write it here, no problem. But you cannot write an answer like this. Okay, if it is a carry, you cannot write it here. In pen and paper, we can just write it here, no problem. See, only if you write the answer, you get the right value. So what is 1, 1, 1? Actually, 1, 1, 0. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. 2 to the power of 1 is 2, 4. 4 plus 2, 6. Actually, the value should be 14. 7 plus 7 should be 14, but we got here 6. If at all we add this number 1, 2 to the power of 3. 2 to the power of 4 is 8. So 8 plus 2 is 10. 10 plus 4, 14. Only then you will get the correct answer. But here what happened? The number of bit has exceeded. Right here, there's only 3 bit. But here we got another 1 bit here. So this becomes 4 bit. But this cannot be handled by computer. So this problem is called as overflow. Okay. So we are getting the result so that we have to remember in unsigned arithmetic, if you have a carry from the most significant bit, what is the most significant bit here? This is the most significant bit. Okay, so if you have a carry from the most significant bit position, then an overflow has occurred. You might ask me, like, why do we need to consider this overflow? We can just simply write this one here, but this is possible only using pen and paper. Okay, so this is not possible using computer. In computer, the memory is fixed. The registers in the ALU, arithmetic and logical unit, are fixed. So all operations are performed on the registers. Like for example, suppose we have a 3-bit register here. Okay, the same arithmetic operation if we perform for 7, 1, 1, 1. And there's another 3-bit register, 1, 1, 1. So this both are called as operand registers, and we have another register that is result register. Even that is a 3-bit register. So what is the answer we get here? 0, 1, 1 and 1 carry. So where will this 1 go? We just have a 3-bit register and this is fixed. Okay, so how will the computer write the other value? So what does the computer say as? The computer says overflow has occurred. Computer has to identify the overflow and it has to rectify this problem. Okay.
Okay.
So, okay. There are through like operand registers, there is 3-bit, and result register also we have 3-bit. So the overflow has occurred and take the only then the computer can take appropriate measures so that the computer operation is performed. Right. So it is the responsibility of the operating system or the compiler. So this is why detection of overflow is necessary. Okay, this is in unsigned numbers. Okay, so if we have a carry out outside from the MSB, most significant bit, if the carry out is 1, then we say the overflow has occurred. Now we'll move on to unsigned number. Okay, overflow in signed number. How do we identify overflow in signed number? So system must detect overflow and handle it. So let's see a few more examples and we'll add 14 for answer. For signed number, let's add 2 numbers, that is 14 plus 14. For example, for signed number, let's see an example, 14 plus 14. So how do we write 14? 1, 1, 1, 0. Another 14, 1, 1, 1, 0. Is this correct actually? Two. Two cents of 15, 0, 2, 3 stars, 6, 1, 2 ones are 4, 1, 1, 1, 0, 1, 2, 0. Okay, this one we won't get carry. So we'll, okay, for signed number, let's take for example 6 plus 8. 6 plus 8. 6 plus 8 is how much? 12, 13, 14. 14 should be the answer. So what is the value of 6? 0, 2 ones are 2, 1, 1, 1, 0. 1, 1, 0 and 0 for positive 6. Okay, this is sign bit actually. So we put 0 here. And for 8, it was like, it was a, for 8, we have a 4 bit 1000. To 8 bit. So this is 1 for this is it, right? 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0. Now even for this you won't get a carry. Okay, sorry, I'm back. Are you there, Shahida?
Yes, teacher.
Okay. So on overflow in signed numbers, there are two conditions. Like if we add two negative numbers and get a positive result, then a overflow has occurred. Right? If we add two negative numbers and if we add two positive numbers and we get a negative number result, then the overflow has occurred. This is the two condition for overflow in signed numbers. Okay, in signed number, this is one condition. And then for unsigned number, we have seen already only one. If there is a carryover, that is, if the number is one, then it is a overflow. Whereas in signed number, if we add two negative numbers, for example, if we add -7 and -7, -7 and -7. So how do we write -7 using overflow? First, we'll find the value of +7. +7 is nothing but 1, 1, 1. And 2's complement for this, since we are finding for sign number, 2's complement for this is write the first one and after that flip the number 0, 0. Okay, so the first value will be a sign, that is 1. Since this is negative number, sign bit is 1. Same way, 1, 0, 0, 1. If we add both the number, what do we get? 10, 1, 0, 10. Again, we get a carry here. This goes here. This is the carry number. Okay, 7 plus 7 is actually 14. So what value do we get? 2. Right, if we add this 1 here, if we put the 1 here, this will become 8. 2, 4, 8, 16. So this will become 18. So that is also a wrong answer. And see the result, it comes in negative. So when we add two negative numbers, so what is the value here? 1, 0, 0, 0, 1. See, 1, 0, 0, 1, 0. This is the value, right? 1, 0 plus 1, 1 plus 1. 1, 0, 0. So it's 1, 2, 0, 2, 0, 0. 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. 8, 8 is 16, 16, 17 plus 18. So even this comes as wrong value. So when the answer comes as a wrong value, then overflow has occurred. Okay, so this shouldn't be the case. So 7 -7 plus -7. Why do we add the answer? Why do we add? Because we found the 2's complement. So we shouldn't subtract, only we have to add. Okay, so the value is not -14. Actually, we should get -14. So we don't get the result. Okay, so so that's why there is an overflow. Okay, now there is a overflow. Can you understand this, Shahida?
Yes, teacher. Miss, why are we adding that
Which one?
-7 and -7? Why are we adding it?
-7 and say -7. See, like we have to add both the numbers. That is, here we have -7 and -7. We have to add this both. Why do we add? Because see, in normal addition, if we do in normal decimal addition, we know that if both are minus value, negative value, we'll add and write, right? We'll add and put the minus sign in normal decimal addition. But whereas in 2's complement, what do we do is we represent minus value. Instead of writing the sign, we represent in 2's complement. Instead of plus sign, we write +7, we write it as -7. So how do we represent -7 in 2's complement? For example, if 7, positive 7 is actually 1, 1, 1. Positive 7 is actually 1, 1, 1. So to write -7, what do? We find the 2's complement of -7. Right. So 2's complement means we have to write in 4-bit. That is 1 bit we have to keep it for sign. So since this is -7, we write -1 here. Okay. To convert this into 2's complement, what do? Write 1 here and flip the digit 0, 0. So what is the answer for -7? This is the answer. -7. Okay. Again, another 1 -7. 1, 0, 0, 1. So this is actually negative value. It is already a negative value. So we have to add. That was what the positive point in 2's complement is we don't have to do subtraction in 2's complement. We'll find the value of negative value and add. Okay,
Okay.
that's why we started to use 2's complement in computer, because we don't have to find the we don't have to do subtraction. We only do addition in 2's complement. Understood? Okay, so when we add both the numbers, what is the answer we get? 1 plus 1 is 0, 1 carry up, 1, 0. 1 plus 1 is 1 carry up. We can't use this here, right? We can't put this here. This is a carry. So what is the first value? What is the first sign bit here? 0. Actually, we added two negative numbers and we got a positive number. So the sign bit is 0 here. So if we add two negative numbers and if the first value, that is 0. Okay, if the first value is 0, that is positive, then we have to say that an overflow has occurred. Okay, so the result is wrong. There is an overflow. Okay,
Okay,
we'll take
teacher.
another example. So plus 6 and plus 5. Okay, so first we saw for two negative numbers, minus 7, minus 11. Now we'll see two positive numbers in signed, overflow in signed for two positive numbers. Okay, what is the value of plus 6? For a positive sign, we put the first bit as 0 and the value of 6 is 1, 1, 0. Whereas the value of 5 is 1, 0, 1. And for positive sign, we write it as 0. When we add this both, 0 plus 1, 0, 1 plus 0, 1. 1 plus 1 is 10, carry up 1. So here we got a negative bit. So 1 is for negative value. So here, even here, the answer is wrong. Okay, so what should be the answer? 6 plus 5 is 11. Here, what is the answer here? 2 plus 0, 1, 2. So the answer is wrong here. So if we add two positive numbers and get a negative result, then overflow has occurred. Since the first bit is 1, so here overflow has occurred. Okay, so overflow has occurred. The result is 1, 0, 1, 1. This is the negative number because MSB here, that is most significant bit, is 1, which denotes that this is a negative number. But actually the result should be positive. This has to be 0. The reason is that 11 is out of range. Why does this happen? Because this is a 4-bit number, right? The range of 4-bit number is actually plus 8 to minus 8. Sorry, minus 8 to plus 7. We have seen already how to find the range of 4-bit number. Okay, according to range of 4-bit number, it has to be between minus 8 to plus 7. So 11 cannot be represented. So now we conclude if we add two negative numbers and get a positive result, then overflow has occurred. And if we add two positive numbers and get a negative result, then overflow has occurred. Okay, there is also another one method that is, here I told you, right? This is the most significant bit. While adding, okay, if carry into most significant bit is equal to carry out of most significant bit, then the overflow has occurred. That is, see for it. Here I did some, right? I wrote it here. See, let me write this clearly. 1, 0. See, 0, 1, 1, 0 plus 0, 1, 0, 1. So when we add this number, 1, 1, 10, there's a carry here. What is the carry here? 1, right? And 1 plus 0 is 1. So we don't have a carry, so we'll consider this as 0. If we don't have a carry, we'll consider this as 0. So carry in is 1 and carry out is 0. If both are different, then there is a overflow. Rahim. Okay. If the carry in and carry out are different, then this is called as that. Then the overflow has occurred. Okay. Whereas if carry in is in and carry out are same numbers, if both are same, if both are same, then no, there is no overflow. Okay, this is one of the different method used to find detect whether there is an overflow or not. Okay, understood? Can you hear me?
Yes, teacher.
Shahida, can you hear me?
Yeah, I
Okay.
can.
So what is it? Second one is if carry into most significant bit is not equal to carry out of most significant bit, then overflow has occurred. If carry into most significant bit is equal to carry out, then no overflow. Okay, this is the simplest way to find whether there is a overflow or not. Okay. For example, if plus 6 and minus 3, if plus 6 and minus 3, you do this and see. Do you have a pen and paper with you?
Yeah.
Do this and see. This will give minus 9 as answer, actually. So find out whether you get this and whether it is within the range. And the result should also be negative. I'm sorry, not plus 6, it's minus 6. Okay, minus 6. What is the value of minus 6? So what is the value of 6?
101.
101, 110. 110, right?
Yeah.
For negative number, we put one more, 1 here. For 3,
011.
yeah. For negative number, 1. So 1 carry. Okay, so MSB is negative. So we get a negative answer. This is 8 plus 1, 9. So we get the correct answer, that is minus 9. Right. And see here, when we add 1 plus 1, 1 carry here. This is carry in, C in. Okay. And again, here we have 1 carry. This is C out. Both are same, 1 and 1. So there is no overflow. If both the carries are same, there is no overflow. Understood? Understood C in and C out?
Yes, teacher.
Okay. So in this example, we don't have an overflow. Okay, any doubt in overflow?
No.
Okay. Okay, next we'll move on to fixed point numbers. Okay, so in fixed point number is the same. Okay, usually when we write a decimal number, right, we write it as any number 2, 3, or 28, or 126. We just write it like this. This means there is a decimal point after the number, right? This is for integers. Integers. Right? In integers, we don't have fractional part. So if we don't have a fraction part, it means that it is fixed. After every number, we have a decimal point. For example, if when we write money, how do we write money? How do we say 1 rupee 50 paise? 1.50. So only two places after a decimal point. We have only two places after decimal point for every representation of money. So the decimal point is fixed and the fractions are just two integers. Right. So this type of representation is called as fixed point numbers. So every time the numbers are, say the decimal point is always kept actually after the same numbers. See here, after decimal point, you have four numbers. Even in the next example, you have four numbers. Even in the next number, you have four numbers. So it is fixed. So it is always easy for computers to do calculations. Okay, if the numbers are fixed like this, if decimal point is fixed, we have some issues with the computer. What are those issues? If it is for small numbers, it is easy for computer to handle. Okay, if we have a register with 4-bit, 8-bit, so the computers will divide it. Okay, for this part, for decimal part, for integer part, half of the register will be given. That is 3-bit will be, 3 or 4-bit will be given to the first part, and the second part will be given to the decimal part. Okay, this will be easier for computer to allocate. Consider if we have very big number. Okay, like 2.3467, it goes on like that, 0000. So how can computer represent this number using this register? It is very hard for computer to allocate bits according to the numbers. Okay, so it is also not very easy to have fixed point numbers. It is also not easy to represent using fixed point representation. So what do we do? So that's why we started using floating point representation. Okay, what is fixed point representation? Number of decimal places is fixed and the position of decimal point does not change. Okay, so what are the advantages of using fixed point? Fast calculations, and it is easy, simple to implement, and it is used in simple devices or embedded systems. Okay, what are the disadvantages of using fixed point? It cannot represent very large or very small numbers. Limited range. Okay. For example, money, when we use money, 123.45, 123.45, always do two decimal places. But you cannot change the decimal values like this and right. This is not possible using fixed point numbers. That's why floating point numbers were used. So why do we use a floating point at all? Imagine we have numbers like this, 1, 0, 1, 0, 0, and 0.00001. These numbers are very different in size. Every number has a different size. So if we fix decimal points for places like fixed point, we cannot handle very big number or very small number. That's why we use scientific notation. Okay. So for example, see, this is a 8-digit number, right? Where I'm saying this in decimal point. Okay. Don't consider this as 8-bit or this binary number. Just consider this as decimal number, 8-digit number. Okay. So what is the maximum number we can represent using 8-digit in decimal plus 8 nines, 99999. And what is the least number that we can represent using 8-digit number is minus 99999. You know this, right? What is the biggest positive 2-digit number? Shahida? What is the biggest positive 2-digit number?
99.
Yes, very good. And what is the smallest digit number? 2-digit number?
10.
10. 10. Likewise, in 8-digit, if we take, for example, we can write it as everything as positive 9999. And for minus 999 in 8-digit number. The smallest, if we go in negative values, the smallest is 9999. Right. Okay, this is what we can represent. But for example, if we wanted to write this much amount of number, see such a long number within this range. So how do we write? That's why we use scientific notation. Okay, using scientific notation, we write it as 1.239 into 10 to the power of 24. So everything comes within the digit. See, how many zeros are there? That many zeros, we write it as power. Have you studied this in maths? This is called as scientific notation. Have you studied this? For
Yes.
example, okay, if you wanted to write 1000 can also be written as 1 into 10 to the power of 3. Do you know this?
Yes, teacher.
The number of 0 will be written as exponent. Okay, this is called as exponents. Okay, so this type of representation is called scientific notation. Okay, even if we wanted to write a smaller number, you see 0.000, negative value. Okay, even for that, we can write like this. See, 0.500 into 10 to the power of minus 26. When the point moves to the right side, we write the negative number, negative exponent. When the point moves to the left side, we write positive value. See, for here, consider this one. Okay, the same example, 1000. Actually, 1000 means actually the decimal point is here. Okay, we have moved it left side. Okay, 1, 2, 3. And we've kept the point here, 1.00, 1 into 10 to the power of 3. So since we have moved it left side, the value is positive. Okay, so if we move the point right side, then the value becomes negative. Okay, that is the difference. Here we have moved the point this side. 1, 2, 3, 4, 25, 26 times. So we got the value as negative exponent. Clear?
Yes.
Understood, Shahida?
Yes,
Okay.
teacher.
Okay. Likewise, okay, so this is how we can represent decimal numbers. Okay. So likewise, this is called as, for example, in the 8-bit, if we write it like this part is called as significant or mantissa. Okay, this part, this alone is called as significant or mantissa. This value is called as significant or mantissa. Okay, just have this in mind. What is mantissa? The actual value is called as mantissa, except the power value. This alone is called as mantissa. Now in this part, this is called as significant or mantissa, and this part is called as base. You already know in decimal, 10 is called as base, and the exponent is actually 24 here. Okay, you should understand the different names used for this. Okay, this is called as mantissa, and this is called as base, and this is called as exponent. Now, in floating point representation, for example, even in binary, if we wanted to represent the same value in binary, we represent it like this. Okay, so this is called as significant or mantissa, and the base is actually in binary 2, and exponent is 3. This is how we represent floating point in binary value. Previously, we saw how do we represent decimal in floating point. Here we have seen how we represent floating point in binary number. Okay, so in binary number 2, we write the same thing, and this value is called as mantissa, this is base, and this is exponent. Okay. So even in binary, for example, as I told you, so why do we write it as 10 to the power of 24 here instead of writing the number like this? Because here we can write only 8 digits. But in this, we have more than 8 digits. So this is called as overflow. Just now we saw what overflow is, right? It has to fit within the digits. If it cannot fit within the digit, then overflow happens. To detect and solve the overflow problem, scientific notations are used to fit within the given digit. Okay, even in computer, we have bits, 8-bit, 16-bit, 32-bit, we have bits like that. And if the number exceeds, if the answer or result exceeds the number of bits, what do? We use scientific notation so that the value fits within the register. Okay, we can represent like this. Even decimal value can be represented as scientific notation. This is called scientific notation. For example, uh, okay, we see here. There's a number 23535.35. Okay, so we can move the decimal point as we wish. Okay, if it moves to the left hand side, we can write it as 2353.535 into 10 to the power of 1. Okay, if it moves left hand side. If it moves right hand side, we write it as -1. If it moves one time, 10 to the power of 1. If we move it twice, 10 to the power of 2. So we can represent the movement of the we call this point as radix in computer. Why do we call this as radix? Because in decimal, we call this as decimal point, but we don't use decimal point in computer. We use only binary numbers. So we call this as radix. Okay. So what is radix? Radix is nothing but decimal point. Okay, radix means if I say radix, radix is nothing but decimal point. Have this in mind. Okay. So we can move accordingly. For example, we can write the value 23555.35 as 2355.535 into 10 to the power of 1 or 593,543.8 in 0.8 can be written as 59.53, 59.35438 into 10 to the power of 4. 0.002453 can be written as 0.2453 into 10 to the power of -2. Since we have moved the point this side, 1, 2. Here it comes, so 10 to the power of -2. If it moves right hand side, minus value. If it moves left hand side, plus value. Okay, so after writing this, each one has a different notation. See, this is 10 to the power of 1, this is 10 to the power of 2, and this is 10 to the power of -2. So computer will get confused, right? It can't, so we need a standard form. We need a normalized form to represent numbers. Each one, if I asked you to write, you'll write it in your own way. If I asked you to write this number, you'll write it to your own convenient way. Okay, so every one of us, each one will use a different notation. We can sometimes we can represent this by 10 to the power of 2 according to the floating value, floating decimal point. We can write it, right? So what people have done, they gave a normalized form. Like everyone, whoever is using computer, we all should follow this normalized form. So what is that normalized form? We cannot write as we wish. Okay, we can write only in this format. That is 1.x666 into 2 to the power of n. So only 1 has to be this side, and after that there should be a decimal point, and after decimal point we can have any number of values to the and multiply to the number of 2 to the power of n. Okay, this is called as normalized form. So every number has to be converted to normalized form. So why do we have normalized form? Because each one of us will follow our own system. Right? Each one will write according to their interest. For example, some will write, instead of writing 1000, 10 into 10 to the power of 2. We can write it like this, or 1 into 10 to the power of 3, or 100 into 10 to the power of 1 or 3, 2, and this is 1. So each one we can write as we wish. Understood, Shahida?
Yes, teacher.
Shahida? So what they have done, IEE, there's a system called as IEEE, IEEE. This is actually an organization formed by a group of engineers. Okay, so what they've done, they asked us to follow a normalized form. According to this form, we can write the values only with this format. Okay, this is the normalized format. We should use only this format. So when we multiply, we have to use only this format. So normalized form is standard form. This is called, this is in decimal. So computer uses this format to represent binary in floating point. Okay. Everything is same in binary except we use zeros and ones. Here we use every numbers, but the same is converted to binary form, that is 0 and 1, and the base is 2. So if decimal moves right, LHS, left hand side, it is positive, and if it moves right hand side, it is negative. The same thing. Okay. So in binary, how do we write? For example, if we write 1 1 0 0 1 0 1 0 0 1 0, we can write it as 11.00101010 into 2 to the power of 9. So for now normalized form for floating point representation, now see this most significant bit. Okay, it has to be non-zero. That is one rule. For normalized form, you should see the most significant bit, that is here it is 1, and it also has to be non-zero. That is very important. Okay. So we can manage big numbers. So how to convert floating point to binary or decimal, we'll see that now. Here 1.100101010